everybody, to Data Science and Technologies. We are the week before spring break. So next week, students will be on spring break, and I will be around a part of next week. I'll probably take a little bit of time off Thursday and Friday, but particularly if you're starting to think about what you'd like to do for your data science project and you might like to chat a little bit, do let me know. Monday, Tuesday, Wednesday, we should be able to find some time. So I'm just going to close the video screen so we can conserve the bandwidth. So this week, I wanted to talk to students about large language models. And let's start off and do a video. This is something I saw on Scripps News, and I thought it was such a nice overview of how these large language models work. So let me see if I can go ahead and play it. And by the way, if you're having trouble hearing it, you can find this video under how chatbots like ChatGPT work. So if you're having any problems at all with the video, just click this link, and you'll be able to go to this same page. And again, let me just double check and make sure that and as I said, I just want to make sure I'm also sharing the system audio.
If you were asked when was the last time you used artificial intelligence like ChatGPT, you might not think of using autocorrect to text or asking Alexa about the weather. But AI chatbots are more common than you might think. We take you through the technology.
Chatbots like ChatGPT use a type of AI called a large language model. They understand text and generate words to sound human.
It's almost boring now to say this, but the fact that I can talk to my computer and have a semi-coherent conversation is like, it's just unbelievable.
Daniel Dugas is an AI and robotics scientist.
As an engineer, I immediately was pushed into the direction of, okay, how do we make something like intelligence?
While AI chatbots may seem intelligent, they essentially just predict the next word, much like your phone's text suggestions. Trained on vast data, it understands conversations and maps out word relationships the same way our brain does. Let's say you type, "Don't put all your eggs in one." Now imagine this process like an assembly line. It breaks down the phrase into numbers called token IDs. Next, the numbers are expanded with more context. For example, take the word egg and plot it on this graph. It sits between chicken and young, but egg has multiple meanings, so more and more dimensions are needed, much more than we can even imagine. The numbers pass through several layers for refinement, giving more weight to the words like egg over the. This is repeated many times. Finally, the process reverses to turn the numbers back into a word, basket. That word is added to the original sentence, and the process begins again. So is it just advanced word prediction? And are there limits?
You have papers saying, a model will never be able to create music, or a model will never be able to answer a mathematical question. And they basically are crushed in the last 5 years.
Experts say AI chatbots are only going to become more human-like in the future, transforming the way we interact, work, and live. Katia Tubman, Scripps News, New York. If you were asked when was the last time you used artificial...
All righty. So, so what are some of the key takeaways from this little video? Well, one thing that is very important is to understand that large language models, they are not having what we call generalized intelligence. They have been trained to predict what they feel are, the most logical grouping of the words. Now, and that is very important. Last semester, we were teaching a course, Dr. Wu and I, on how to develop a research proposal. And we did have a lot of students using AI to help them write portions of their report. And that in itself is not a problem as long as you understand that large language models are not generally intelligent. They are basing their, I want to say their predictions on what they have been trained on. And that's very important. If you are using a large language model that has been trained on data from 2 years ago, you're not going to necessarily get the most recent information. The other thing is that where we could spot that a lot of students had used a large language model was that a lot of students cited references that when we used another AI-related tool, the Google search was not able to come up with that article. And that is something to remember, that an AI tool, the reason it will hallucinate is that it may just, in predicting the probabilities, it may come up with something that really doesn't match something that exists in reality. And I think a lot of students got fooled because the references that the AI tool produced were very realistic references. They had names of authors that, were very familiar. They had titles that looked familiar. They had journals that looked familiar. They had volumes. They could even produce document IDs that all looked very familiar. The problem is that when you put all those things together and said, is there an actual article that you could have read with that author and that title coming from that journal at that time with that document ID? The answer was no, it doesn't exist. And so that is why when you're using large language models, you just always have to keep in mind this probability aspect. Okay, and so that's something important to keep in mind. The other things to keep in mind is that not only is it very intensive to train and develop these large language models, but you can see from that video that assembly line involves quite a bit of computations. And so that's another thing to keep in mind, is that large language models, depending on what you want to do, may not be the best tool for the job. It may be that particularly, let's take a simple example. You want to add 2 plus 2. A calculator, can do that job very quickly and efficiently. So part of what we're going to talk about is, what's the right tool for the job? Do you need a small hammer? Do you need a bigger hammer? Do you need a sledgehammer? Do you need a jackhammer? So knowing what is the right tool for the job is very important. This is also something very interesting. All this, computational energy, if you will, that is needed to use AI. This is a kind of very interesting thing. One of the things I'm doing over spring break is I'm talking to my financial planner, where do I want to put some of my retirement funds? And one of the areas that I've gotten very interested in is, if AI is going to be really huge, it's going to need a lot of energy. So we had mentioned this. This was a CBS Sunday morning story. The fact that there's sort of renewed interest in not only nuclear energy, which is essentially fusion. That's right. I think nuclear. Let me put it this way. I believe nuclear energy is actually fission. And there's a lot of of research into fusion. I always get those two confused. But I believe nuclear energy is essentially a fission, but fusion, while they just recently had the first lab test where they were able to generate more energy, slightly more energy than what it took to create the fusion process. And so there are some predictions that maybe in another 10 years or so, we might actually start to see the first fission reactors. But very interestingly, there was an interesting article on how even, for example, in Pennsylvania, this was the article. Here, I'll put this in the chat bot. So not to give stock advice or anything, but check this out. Microsoft is paying $1.6 billion to restart 3 Mile Island, which is a nuclear power plant close to Harrisburg, Pennsylvania. And the reason why is, big tech companies want to have, in order to make AI data centers, they need huge amounts of electricities. And you can't do that with, wind or solar or, so if you want to be more green, nuclear, modern nuclear is maybe the way to go. And so this is kind of interesting. I was thinking, rather than bet on a particular technology stock, because you never quite know who's going to be upended by someone else. If you figure that maybe a common denominator, that whoever comes on top, they're going to need vast amounts of electrical power. Maybe that's the place to invest. I'm going to invest in electrical producers. Maybe that's the surer thing. So I may be completely wrong about that, but there are some interesting implications of where AI is going, and thinking about those things is something that is all individuals as well as organizations and nations are going to have to think about. Okay, but that first little article is a nice little overview, just a conceptual overview of how a chatbot would work. So let me pause for a moment and see anybody has any questions or comments.
Dr. Pierce, I think I might have a question. I just don't know if it's the right kind of technique. How are the LLMs different than Markov chains, where you would just look at the statistical implications of what the next word would be given a large enough body of writing? Are they basically just different because they use so many more different, I guess, descriptors to describe how words are related rather than just statistical probability that you would see in a Markov chain?
Right, and that's a very good point, because when it comes to predicting the next word, there are several techniques that will do that. For example, you can use text mining to do that without involving an LLM. There are statistical models like the Markov chain that you could use to predict the next word. And again, that does not involve an LLM. So I think you're hitting on something when you say, I think it's the architecture. I think when you look at the use of the creations of these embeddings And first of all, the algorithms used to process vast amounts of data to create these embeddings, and then the algorithms that are used to mine these embeddings in order to make its prediction is sort of what makes these large language models special. And I think it's essentially based on their flexibility and versatility, and some of the things that we've been able to not only, like for example with the large language model, not only can you get it to predict the next word, but you can go a step further and have it predict a string of words, which creates a sentence, and then sentences can create paragraphs, and then using things like we'll show you a resource for prompt engineering. You can get large language models to generate conversations, to generate reports, generate essays, to generate a whole body of work that is essentially goes beyond what you would normally be able to get from like a Markov chain. But in terms of predicting the next word or the next couple of words, yes, there's any number of techniques that are existing that will do that. But I think the large language model takes that capability a number of steps further. Okay. And this second model that is in our class materials for this week has some great, I think it has some very nice explanations. So when people talk about this whole AI, we start off very, very broadly, and we get into, for example, within that whole idea of broadly defined intelligent machines. And so I think, for example, Daniel, that you could almost use things like the Markov chains and a lot of the statistical techniques that we use in order to draw insights from data, to be able to make predictions and inferences and classifications based on our data. So, think about, we started with statistics, and we started with, looking at just well-known techniques that go back many, many decades, like regression. Those are all, in a way, a form of a broadly defined a way of getting a machine to learn from the data and to make some sort of prediction, or be able to explore our data, or look for patterns, and be able to draw insights or from our data. And then you'll notice that you get into the more sophisticated machine learning, is learning general patterns from the data. So now you get into techniques that are using sometimes they're using sort of a systematic technique to work through the data in order to find patterns and associations. So now we're talking about decision trees. We can be talking about cluster analysis. We can be talking about basic neural networks. We can talk about genetic algorithms. We can talk about case-based reasoning. We can talk about a whole host of different, random forest, XBoost. You can kind of go through the list of a whole host of machine learning models that help us to seek out patterns. And then you get to deep learning, and often this area, this inner circle, is dominated by the use of advanced neural networks that really allow you to work with unstructured data. So for example, when we did that lab exercise when we were trying to identify handwritten numbers. Notice we were using a particular neural network called CNN, convolutional neural network. And so that's what you see in this deep learning space. Various types of neural networks that help you be able to look for patterns, within the pixels. Or, maybe you have another type of neural network that is looking for patterns within text or patterns within audio. And then notice right in the center here, now in the berry, you have this smaller circle, which is learning to understand natural language. And that's the large language model. Okay. And so they've got some, of course, they have a little bit of explanations about these different layers. So let's take a look. So let's start off with, rather than just looking at things like statistics and linear regression and hypothesis testing, as they say, many of you, if you've taken a Stats 101 course, have seen some of those techniques. But let's go to the next level, which is the machine learning. So how do we use non-statistical, but a different approach to be able to look for patterns in our data? So here's an example that is using, a form of cluster analysis. So here they give the example of two genres of music, let's say reggaeton and R&B. And what they have is, let's take a look at in practice, is, see if I can make this a little bigger so you can see it? Okay. So notice here, if we just had those two forms, R&B songs and reggaeton songs, and let's say these two genres were distinguished by their energy levels and their tempo. So this is just very simple, just a, 2 dimensions. And notice in the blue dots are the R&B songs, and you'll notice here the yellow dots are the reggaeton songs. And so you could, so if you have, for example, 20 songs, and let's just say we can go through, and you can imagine, in this case, it is that you could almost draw a linear line, couldn't you? A diagonal line that would kind of separate the blue dots from the yellow dots. And then if a new observation came along, you could kind of say, well, if that new observation is, below that diagonal line, meaning it's in the blue dot space, we would classify it as R&B. And if that new observation is in the upper quadrant, where the orange and yellow dots are, we would classify it as a reggaeton song. So that's an example of how we could use machine learning to classify. And so notice we're using, if you will, we're starting off with basic statistics, with a 2-dimensional scatter plot. And then we're just building on that, how we could use a machine learning technique like cluster analysis to be able to train a machine learning algorithm on a larger set of data to basically come up with how to classify. Now, where things can get more complex is, sometimes when and again, we were just talking about 2 attributes, energy and tempo. You can imagine, well, in real life, I might have a lot more attributes that I need to be able to use in the classification process. So you can imagine once you start to go to 3 attributes and 4 attributes and 5 attributes and 10 attributes, you can understand that this is where you can't use that simple scatter plot anymore. And you can also see that a lot of times there may be a difference, but maybe it's not a linear relationship. Maybe it is something that is an S shape, or it's got it's got some curves. You can draw a boundary among those different attributes in whatever n space it is, but you can imagine it's not a simple straight line. So again, what we end up is, in that case, as things get more complicated, you can kind of see, we start off with simple statistics. We get things more complicated than statistics can handle. So we end up going to machine learning techniques. And that can be great. But eventually, what we want to work with is even more complicated than a lot of machine learning algorithms can work with. And then so we end up having to invent a new technique to give us the flexibility that we need. Okay. But in essence, in machine learning, what it does is notice here, let's suppose we are just dealing with 2 attributes so you can see the picture. And again, we've got the blue dots and the yellow dots. And all of a sudden we have a new observation, and we now want our model to make a prediction. Well, what type of song is this? And so what we do is we would use our machine learning algorithm, and what it would do is it would say, okay, what's the probability that this observation belongs with the R&B songs, and what's the probability that it in fact belongs to the reggaeton songs? And what it'll do is it'll figure out, who has the highest probability of belonging. And if that class 2 is R&B, then that's what it's going to predict. Okay. So we mentioned, the best way to separate, again, it may not be a simple linear function or a simple mathematical function. And then, as I say, often we have lots of input variables. And we often have more than 2 classes. We don't have just 2 genres of music. We may have dozens and dozens and dozens of genres of music. So think of things like Spotify. Okay. And then we get into other questions. Again, this is why we started to go into deep learning and convolutional neural networks. What if your input is not numerical attributes? What if it's an image? So here's the question. We feed an image. We want to know, is this a tiger, a cat, or a fox? So ideally, what we like to do is take this image and put it through some sort of algorithm that will tell us, 96% probability that we think it's a cat. But you'll notice that often, and we saw this even working with simple handwritten number, even a 28 by 28 pixel image is over 700 pixels. So again, you get into the fact that particularly if you're working with a color image, not only do you have the one, if you will, the one array of pixels, but if you're doing color, then that means you have an array for the red, an array for the blue, and an array for the green. So you'll notice for just one image, you could easily, you know, a 224 times 224 pixel image, just one image over 150,000 pixels. Okay. Okay. So, and another example is if the input is text and we want to, if you will, again, kind of predict the sentiment classification. Okay, the movie was great. Again, you know, we have these these word embeddings represents a word's meaning in its context, and we'll take a closer look at what that means. But if you take a look, you know, these embeddings are just taking each word. Let me see if I can make this even bigger so you can even see this. Let me try. Oh, I know what I'm going to do. Let me see if I can get a better image this way. Let me see if I can. Let me see if I can do it like this. How about this? Get rid of those headers. Oh, this might be a little better. Okay. So you'll notice that, and this is very similar when now we're getting closer to what they were talking about in large language models. They take each word, the movie was great, and they create these vectors which represent various attributes or contexts associated with that word. And then we have some sort of numerical rating associated to how much that word is fulfilling that particular context among the multiple contexts that we have associated. So you can kind of think this had 1, 2, 3, a bunch of others, and 4. So we, as I say, we have a bunch of different things that we want to capture about the, and each one of those, whatever those things are, whatever one of those attributes or contexts are, we've got some numerical rating. Okay, and we're going to use those embeddings to help us process it through some sort of algorithm that, again, is going to use those embeddings to come up with a prediction. Is that when you hear the movie was great, should you take that as a positive sentiment or a negative sentiment? And here, it's more likely to be positive. So that's what the model would predict. Okay. So typically, again, we're starting to say, well, how would we capture the word semantic and syntactic meaning? Okay. And as I say, these embeddings are typically done through the training of the machine learning models. Okay. So, so basically, what we're trying to do here, and I'll have another reading that helps to explain this, is you're literally taking the sentence and breaking it down into the words and turning it into a sequence of numeric inputs. And that's essentially what's called the word embeddings, which are capturing the various meanings associated with that word. Again, then this can be fed into some type of machine learning model. But again, it could be a large language model. Maybe there are other types of models that can work with essentially these word embeddings. So you'll notice here, you know, for this sentence, it's 1, 2, 3, you know, 4 words, and each word has a list of those, you know, the things that we want to capture or represent about that word, and the numeric measurements then create that vector of numeric information about our sentence. Okay. Okay. And again, language is very complex. Just think of something like, that was a great fall. Now, again, is that meant to be positive? Is that meant to be negative? Is that meant to be sarcastically? And again, the idea is, we were trying to represent what we wanted to do with an ML, but notice the question mark. Yeah, like have a nice trip. What does that mean? Really kind of depends on the surrounding context. So you'll notice in all these boxes, we know we need some sort of algorithm. And notice the ML question mark, meaning we can try to do this with traditional machine learning, but they may not work that great. And so we may reach a point that we need something even more powerful. Okay. So so the idea of the neural networks is, as I say, and by the way, I was going to say with neural networks, I see that kind of transcending machine learning into deep learning, meaning if you have a very simple neural network, meaning just an input and an output, and then a very simple layer, it's not that different than trying to predict, like using a regression model. So it's interesting, the smaller neural network could almost be considered a machine learning model. And in fact, a very, very simple, just an input and output, and let's say intermediate node, that essentially can even reduce even further, that it's no more complex than a regression model, and even in fact a simple regression model. But as you start to add more layers, and within each layer, if you start to add more nodes, what that does is it provides you more and more ways that you can look for pattern within your data. So if you look at this conceptually, this first are your inputs. So these are the various things about your image. So these could be the various pixels with your image. And then you'll notice that you have these lines coming from the pixel into the various nodes. So you can see that input, first of all, an input can go off to several different nodes. And then you'll also notice that each of these intermediate nodes can receive inputs from one or more pixels. And you can think of these nodes as taking information from the input data, and in essence, taking the weights that are assigned to the inputs and coming up with a mathematical function that can kind of decide whether the information is such that it wants to pass it, to the next node in the chain. And the thing about having more of these layers and more of these nodes is you get more and more flexibility in terms of, if you think of an image, taking different pixels in different combinations and looking for patterns. And if that pattern, when it's evaluated via the function, is deemed to be a significant, you can then basically take those smaller patterns and build them into bigger patterns, and basically be able, in terms of your output nodes, to be able to say, oh, this one output node is, is it a dog? And there's only, a 0.03 that it's a dog. And this next output node is, oh, it's a cat. And we see that's 0.96. And, if there was a third output node, hey, is it a bird? We notice that it only has a 0.1. Okay. Now, it's very interesting. The neural network was meant to pattern the way the brain takes electrical signals into a neuron, and then how the neuron kind of processes those signals, and then how it then elects to decide whether to fire off a signal to the next neuron in the chain, and how it would replicate this multiple times. So our brains, for example, see that image and say, oh, we immediately recognize that's a cat in a bag. And it's fascinating. Our eyes took in that image, and a whole bunch of processing went on in our brain, and it outputted, cat in a bag. And this is a really fascinating thing. GPT-3 has, what is that, 175 billion neurons in order to recognize, like cat in a bag. The brain has 100 billion neurons. So, and interestingly enough, our brains don't need nuclear power to run. So this is really fascinating. I mean, I think we still have a long, long way to go in terms of AI and making it really efficient. But anyway, those are some interesting comparisons. Another way I like this is, one way you can think of a neural network is maybe multiple layers of linear regression stacked together, with the ability also that the relationships could be nonlinear as well. So that allows us to handle not only a vast array of different inputs and all kinds of different combinations, but also to handle the fact that some of these relationships could be nonlinear as well as linear. Okay. And as I say, as the neural network layers get deeper, that's when they transcend from being a simple machine learning, say a simpler machine learning technique into a deep learning technique. Okay. Okay. Okay, so let's take, let's just say, so this has a nice explanation of the language modeling. So, and Daniel, to answer to your question, can you frame language model as a machine learning problem or a statistical problem? Yes, you can. And basically, it's a form of classifications. Okay. And really, it's the fact that with a large language model is that now instead of just having a few classes to choose from in terms of what's the next word, let's say we want as many classes as there are words. So let's say we want to choose from 50,000, So as I say, this is where traditional statistics and machine learning breaks down. Works great if the next word is only one of 4 or 5 words, or 10 or 12 words. But what if the next word could be like one of, as I say, thousands? Okay. And again, this is a nice starter article because it's making things very simpler. There's a lot more details here, but when you first look at that, you just want to start off with the simple. Okay. So, of course, one of the things a large language model needs is massive training data. Okay. We need to have vast amounts of sequences for training a language model, and part of that training is going to help us create the embeddings that we're going to use. Okay. And it's kind of interesting. We'll see that a lot of times we're using sort of neural network techniques in order to create, to figure out what those embeddings should be. Okay. So after training, the idea is now we have this large language model where we can put in a sentence, what is the next word? A trained language model can, that's our input. We're going to feed it, into this large language model, which is now this, has this, complex array of embeddings and the algorithms for essentially using these embeddings to kind of try to figure out what would be the next logical words to complete that thought. So notice here, and notice we're going to chain these things together. So like the next word could be generate. A trained language model can, okay, let's say we go with generate. And then the next thing we say, so what would come out of after a trained language model can generate? Well, then maybe the next probable word might be coherent. Okay. And so this is the idea that with each word that you add to the sequence, you feed it back into the LLM and predict another word, and you keep going until you can actually generate not just a single word, but text. And other things that are sort of interesting about large language models, you don't necessarily always have to predict the most likely word. So for example, you might say, well, maybe when we want to be more creative, what are, say, the 5 most likely words at a given time? So this is the idea of how some LLMs allow you to kind of choose how deterministic or creative you want to be. Yeah. Yeah, go ahead, Daniel. Or Damien, sorry.
Yeah, I was thinking about that. I had a question about that. Like, so going back to like the Markov chains, at some point, the computer is simply generating a random number or choosing from the most popular ones, or maybe there's a weighted average and you're doing a random number, but you're still picking more or less randomly. Like, at what level do you have the ability to determine whether it is, like, because it's not deterministic, so that every single time you ask the same question of ChatGPT, you get the same answer. It's never, it's not like that. And I don't think we want it to be like that. But at what point does it come down to just a random number, like just a random number generator making words that have a good chance of just sounding good?
Yes, and I'll just say that is a really good point, and it goes back to why the thing about large language models, you hear things, well, it hallucinated, meaning exactly what you said. It put a bunch of things together, but what it put together, while it might look realistic, doesn't actually match anything in reality. And there's been a lot of work done in terms of how do we further improve large language models to, for example, to be able to recognize what is fact versus what is opinion. And this is the thing, these large language models really aren't, they still require a lot of human supervision. So when you use a large language model, you still often need someone to review what is produced, and if you will, to kind of fact check it, to make sure that what it produced is suitable for use to the next receiver. So that is, usually it has to be fact checked. Before you would want to hand that generated report to your professor, you would want to read it and fact check it to make sure that it doesn't include any false references or it hasn't missed the mark on any of the sections of the report. Or if you were using the LLM to produce something that you were then going to feed to another LLM or feed to another part of your business process, you'd have to say, yes, is it of sufficient quality to be fed to the next stage? And it's interesting, if you look at ChatGPT, the GPT means the generative, the G means generative, it means next word prediction, and P means it's pre-trained. The LLM is pre-trained on massive amounts of text from the internet and other sources. So that's important. When you use ChatGPT, you are using a large language model that has already been pre-trained. And then transformer refers to the neural network architecture that was introduced in 2017 that basically allows you, to get, answers to your prompts. And again, this transformer is, again, even this article says we won't go into any more details here because what's very interesting is that people can develop applications on a LLM like ChatGPT, and they are actually they're trusting or relying on, for the LLM that they're using, they're trusting that it's pretty good at next word prediction and that it's been pre-trained on reliable sources and that, the neural network architecture that, has been used, has been, executed well. But what does it say is that the transformer architectures work so well because it's focused its attention on the parts of the input sequence that are most relevant at any time. And again, part of this transformer, I think, is also, as I say, the LLMs use a lot of neural networks. I know they use some neural network technology to create the embeddings, and I'm quite sure that the LLM itself, because they represent it as a neural network, means that when you go to use the LLM, it is essentially a very sophisticated neural network that is taking those inputs and feeding it through its neural network in order to, produce those probabilities. So it's kind of interesting. I think the LLMs, my understanding is they're using a lot of neural network technologies, and they're using it in several phases. So let's take a look of how this, a little bit of works. Is that we've got the pre-training. You get massive amounts of data from the internet, books, whatever you're going to feed, whatever text you're going to feed as your training data. And what you get out of pre-training is a model that can babble on about anything, but it's probably not aligned with what we want to do. And then instruction, fine-tuning, you got to teach the model to respond to instructions. Models learns to respond to instructions, and the alignment is a big research topic. And we even see that when using a large language model, a lot of students have chosen, the prompt engineering module in text analytics. And that is very true. Even when you go to use a large language model, how you craft your prompts makes a huge difference in the quality. And then you've got to do reinforcement learning from human feedback. And this helps produce output that is closer to what humans want or like. this talks a little bit about what goes on during the pre-training, and a little bit about what goes through with the fine tuning and the reinforcement learning from human feedback. Okay. 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 So some of the things is 3 examples to test our understanding. So some of the things that LLMs can do well are the text summarization. So this is an ability that they feel probably comes during the pre-training. How about LLMs doing things like chatbot question answering? This is the result of improving the LLM further, not only through pre-training, but through the fine-tuning. And then, yes, where does LLMs either answer things wrong or make stuff up? Okay. Okay, so they talk a little bit okay, so one of the issues that comes up is the LLM doesn't know the answer. There is a tendency for it to just make one up. And so some of the things to be aware of is LLMs are typically trained to generate human-like text, not true text. Nothing indicates truthfulness to LLMs. Usually we need to, this is what people are talking about when they talk about like trying to give an LLM some grounding or a knowledge base so that they don't make stuff up. And this is why also in prompt engineering, it also helps to include a lot of context in your prompt to help the LLM reach a good solution. Okay. Let's see, what do they say about, yes. And as I say, this is, for folks interested, particularly folks from the computer science side, trying to figure out how you can improve those LLMs architecture so they're less prone to hallucinations over time. You'll notice this is an active area of research. Okay. And they give a kind of example. Like suppose you ask Bing ChatGPT, who's the current president of Colombia? Couple reasons why you might get the wrong name. For example, if Colombia just elected a new president, it may be that the LLM may just not know. For example, it'll give you either the old name because it takes a while to train, so it may not have been recently trained with that new information, or sometimes it'll kind of guesstimate based what it thinks is the most likely name, and that could be a wrong or even a fake name. And that is why with prompting, sometimes you have to kind of help out the LLM by saying, referring to this Wikipedia article on Colombia's recent political history, what is the president of Colombia? And notice there the LLM might be able to answer it correctly because now you've given it some information that does have the right answer. But this is kind of interesting. Again, this is kind of a simplistic example because you might say, well, look, if I have the Wikipedia article, why would I even waste time with the LLM? But that kind of though, can give you an idea of when you're trying to build these LLM applications, how important the designing of the prompts can be. Okay. Some of the things, though, that have been very exciting about large language models is sometimes they found that these large language models can perform new tasks without even some previous examples. So, you know, giving it things like translate from German to English, but use only words that start with with an F. You know, that's kind of interesting. It wasn't specifically trained on that task, and yet it's somehow, you know, through its embeddings and neural networks was able to come up with an answer. The other thing is that it's often able to do things with just a couple, what we call few-shot learning, with just a few examples. Standardize different currency formats, and you give it some examples, and then it comes up with a suggestion. Okay. So again, this is a nice article that also, you know, again, this kind of leads to why certain types of prompt strategies seem to work better in getting the LLMs to produce. And so one of the things in prompt engineering is often, if you have a complex task, is to have it break its process down step by step. And so, so it's interesting. Telling the LLM to break things down in steps seems to help its performance. So anyway, this is a nice article to take some time and kind of look through in depth. But I just wanted to kind of go over it broadly, just so you can kind of see where we've been going in the class. You know, we started off with basic statistics, and then we started to talk about text mining, and we got into, you know, the neural networks, and now we're talking about the how large language models work. Okay. And I've been talking about these embeddings, and I found this nice article. Let me just see if I can. Okay. So again, embeddings are not exclusive to just large language models. Other types of AI systems, other types of machine learning tools might use embeddings. And let's take a look at some examples of how embeddings work. Okay. So here's a nice little example here. So let's suppose, let me put it this way, what we're really coming down to is that our computational models really cannot work with text, with our language, intelligibly in their raw format. They really need us to take our language and put it into some numerical data as input. And notice here is typically they use neural network embeddings to convert real-world information into numerical representations called vectors. And vectors are just an array of numerical values that represent information in a multidimensional space. And that is what helps, you know, those machine learning and AI models to find similarities among sparsely distributed items. Okay, so let's take a look at some movies and TV shows. Okay. Again, let me see. Can I make this a little bigger so you can see? Okay. Okay. So notice here, we've got, let's say we've got some releases from, Netflix. It could be a movie, could be a TV series. And what we have is, let's suppose we just have 3 things that we're going to use. And again, in real life, you would have maybe hundreds or thousands of things you're trying to capture about that movie or TV series. But they're just going to do genre, type, and release year. So we've got the conference. That was a horror, released in 2023. It was a movie. The upload was a comedy, released in 2023. It was a TV show, season 3. Tales from the Crypt, that was the horror genre, released in 1989. TV show, season 7. Dream Scenario, that's a horror/comedy. 2023, it was a movie. And you'll notice some things like the release year is already in a numeric format. But things like the genre and the type, movie, a TV show, those are not numeric, okay? So basically what we need is, and this is where they'll use sort of a neural network process to create these vectors that are essentially taking non-numerical data and putting it into a series of values that our AI ML models can understand and relate. So let's suppose we run this through and we say, okay, show me what the vectors would look like. So notice here the conference, you recognize the 2023, but somehow it has come up with 1.2 as the genre rating, and it has come up with 20.0 as the type. Okay, and then for upload, the genre has been converted to 2.3. We see the 2023, but the type is now, a 35.5. And then Tales from the Crypt is a 1.2, 1989, and it has converted the type into a 36.7, okay? And Dream Scenario is a 1.8, 2023, and again, it has assigned it a 20. So, so if you, for example, now you can say to the ML model, what shows are most similar to the conference in terms of genre? Well, it would say, okay, the conference is 1.2. Tales from the Crypt, which was also the horror, that's also 1.2. And you'll notice its third choice is that the Dream Scenario, which is a horror comedy, is closer to the conference than, let's say, the upload, which is a 2.3. Okay. And again, you might say, show me movies, and notice the conference and Dream Scenario would be considered more similar because it is, they were both movies. So anyway, it's those embeddings that kind of form the backbone of how we have taken all of this language and converted into these vectors. And notice you could probably have multiple, as they say, your arrangements, your architecture could probably be augmented, depending, first of all, how many attributes you want to capture, but how many, different ways do you want to combine and basically how you want to represent the information, into these vectors. Okay. And you can have a very simple vector, apple, orange, pear, and the prices. Apples are, $5 a bag, oranges are $7 a bag, pears are $10 a bag. However, notice here, you don't have much other information about apple attributes versus orange attributes versus pear attributes. So, so typically, with a simple embedding, you're not going to find similarities, or you're not going to be able to compare these items to vegetables. Okay. Okay. And notice there are several approaches to how you can do embeddings. There's principal component analysis. There's something called similar value decomposition. There's word to vec. There's BERT. And engineers typically use some form of neural networks to create the embeddings. And so you notice here, we feed it with some vectorized samples, then they learn from the patterns, and then there's fine tuning. And eventually we want to get to the point that these embeddings can, operate independently, allowing the ML or AI models to generate recommendations or respond to prompts from the vectorized representations. And then, of course, this is ongoing to monitor the performance and fine tune. And notice here it ends with a commercial, because Amazon has services to help with the creation of these embeddings that can then be used by the large language models. And I think we've just got a couple of minutes, so let me just show you one more thing I want to take a look at. Just see. Okay. Okay. Let me see. Okay. So on Thursday, we'll say, okay, this is great, large language models, I'm reading the background, I'm getting a sense of large language models, but what can I do with a large language model? Aside from, playing around with ChatGPT and asking it prompts and getting it to tell me stuff, what are some really neat applications that I can build with large language models? So this particular article gives you some of the ways that companies are experimenting and coming up with large language model applications. So assisting with clinical diagnoses, mapping cybersecurity regulations to policies and controls, expediting claim processing, tracking and analyzing customer feedback, fielding customer service questions, enhancing developer productivity. I mean, a lot of our students do, when they're trying to create their, software projects, they're, using large language models, trying to detect signs of malware, trying to, again, provide customers with immediate assistance, troubleshooting equipment issues, summarizing application details, automating customer relation tasks, answering questions, helping with scraping online data, helping with market research, helping with analytics. In this case, being able to ask questions about performance of marketing campaigns in natural language and receiving answers, creating semantic maps, curating scientific literature, helping to helping to build an internal knowledge base, brainstorming marketing content, and generating test data. So take a look at that article to get some ideas. of what you can do with a large, what is a potential application you could build from a large language model. But then what we're going to do on Thursday is we're going to say, okay, but how do I actually build these applications? I know how I would build a tic-tac-toe game. How would I build a large language model? Well, you would probably want to have a large language model application developers tool. So we're going to take a look at one of those tools called LangChain. We'll show you some tutorials, and then wanted to show you some of two really great talks we've had this semester. This talk, and I invite you to take a look at this. This is the Windstream AI workshop that was February 26th. So if you missed that, you'll hear about how Windstream is using AI. And then just this past Friday, Yogesh Pandey, CEO of Hexonica, talked about AI in your future careers. And they use LangChain. They also use some additional tools. The other thing we'll do on Thursday is we'll look at some of the additional AI readings. We'll look at the AI assignment. And then last but not least, if we still have time left in the period, we'll start talking a little bit more about questions about the data science project report and presentation, just so you can go off to spring break with some things to think about. Okay, so that's where we are. We're out of time, and we'll resume on Thursday.